Welcome to Renaissance Charge Videos. I'm Rick Friedrich. So today we're going to show the instructions for the DualPole kit and go over everything that we went over in the last couple of videos. I'm going to replace those videos because I want to put it all in one place, and we want to add a few more things and maybe slight corrections to the previous video. So I apologize if I'm repeating some of these things over again, but what I want to do is make a video from beginning to end and then go over a couple more things. One of the things that I haven't shown is using the variac with the resistive loads instead of the capacitive loads. So I want to show some of those differences and even get a little bit into the third stage process. And so I want to go over a bunch of things progressively here. So I think it's important to start from the beginning because there's many people that don't understand this technology at all. So we want to start off with some very beginning things. So first of all, I want to mention that we have a new book that comes with frequency generator and these coils and miscellaneous parts. The book only comes paper with the kit. There's no digital copy, and there never will be. Anyway, this book goes over some of the details of the motor, and it explains a lot of the free energy systems, and there's a lot of information in it, and I don't need to go into, well, I should mention a few more things. So the book was divided up into two major sections. One is the instructions for the kit itself and the details that you need to know on a basic level. I made this for some of my relatives are 11 years old, and I wanted to give them something. So I made this book and this kit for people that were that young with some assistance. And then I also have a second section, like endnotes, that is, gets into the really advanced stuff. So you don't need this book for the motor kits. They help. There's some information about it, and we'll talk about that throughout this video. But I just wanted to mention this. I'll refer to it from time to time in this video. So what do we have here? Do we have the capability of producing more energy out than in? This is the big question. Has anyone ever demonstrated that? What does that really mean? I cover that kind of subject in this book, of course. So the question is, where's the energy coming from? When you talk about a free energy process or a motor or whatever generation system, automatically people will say, well, that's impossible. You can't get something out of thin air or nothing. And that's not what I'm claiming. They also will say, well, that's perpetual motion, blah, blah, blah. And actually, I'm going to say, that is what I'm saying. There is perpetual motion. In fact, it's absurd to deny perpetual motion. And don't hear me out here. I'm not talking about this motor running forever and not wearing out. I'm talking about the fact that everything is already vibrating. It's already in motion, and that's well acknowledged. So if that's the case, what is making it in motion? Where is that energy coming from? And we don't need to really get into that at all but I just thought I would throw that out. I try and avoid getting into the theoretical, but the book gets into that. I'm a practical guy. I want to see energy work for you. And the bottom line is, people, that the energy is abundant around us, and it's not really that mysterious. You know, I'm the guy that tries to demystify all these things. So what I'm trying to say is that the way we normally run our circuitry, and we're going to talk about it in the loving path systems here, the teaching. The thing is, we normally run our circuitry inefficiently. So we're wasting the energy, and that's the problem. It's not that I'm trying to collect energy that doesn't exist or make some claims like that, but the truth of the matter is all the energy is received pretty much in the same way from its local environment, and depending on how we try and tap into it is more or less efficient or inefficient. And so that's the problem, is that is the wasted energy that we're doing. And so what I'm going to show here is a number of ways to be more efficient. And you know, if I was to say to you, well, I said to a guy a couple of weeks ago, I said, you know, I'm going to show you something where you can get energy from the sun. And you know, the guy would laugh. He was like, well, I already know about that. It's already been discovered. You're not the first one to tell me that, and you know, it's been for a long time. But so let's go back 100 years now and say I had that conversation with somebody and I showed them. They may say, well, I don't believe it's possible, and what you're saying is ludicrous, blah blah blah, and they might give you the whole rundown, just like they would about any of these systems today, saying, oh, well, you know, we're not used to it, therefore it can't be true. The establishment's not using it, so then it can't be true. So now I will say that there are thousands of people all over the world that are using these kinds of systems, and long before I was even born. So this is not something readily available to the public, or that the public is very familiar with, but there are many people and agencies and what have you that are using this kind of technology. But what I'm trying to get at is the kind of energy, what I'm trying to show in these systems is, yeah, a new twist on things, but I'm also trying to show you what's already known and already established. That's what I did with this resonance book. You know, the mysterious word resonance, which is, by definition, a gain system, isn't really clearly understood. So that's why I wanted to really get into that in this book and show what's already acknowledged, apply it in ways that are conventional even, and you know, go back to Faraday and so forth, and show exactly what you can get, and help you to rethink what you already know. And that's the thing, is organizing things. So if you have a big subject matter and you only focus on a sliver of it, and then from year to year, over a century, that's the whole focus, that little sliver. Everything else is just not paid attention to, not focused on. Then you begin to think that this is it, and that's what's happened in electrical theory. It's not that the theory doesn't cover other things, it's just these kinds of processes, they do. It's just that you're not familiar with it, you're not using it, so therefore you come to think that that's it, right? So with the book, we really went into that. The motors, I've been showing this kind of thing for years, and it's all kind of the same thing. But I wanted to bring that up to help, with that. So, with the thinking on the subject, because I'm just trying to really introduce here these ideas for the first time for some of you. This is not like your regular video. There's no videos like this on the internet at all, where it goes from beginning to end and it demonstrates the system. And these are systems that I've been selling for about 13 years now, or making them available for people, showing them how to do it. So this is not something that I just came up with. Now, in this video, I'm going to show some of the latest things that I came up with, and that. So we're going to get into. I've been delayed on shipping some of these motors because we upgraded the code in the Arduino. So, but before we get into that, let's go over some basics. Now, I did a video series about 2 years ago called Selfish Circuits and Loving Paths, or Selfish Unthankful Circuits and Loving Giving Paths. And we're going to show a contrast between the way normal circuitry works and how inefficient that is. So we call that selfish. And it's kind of I'm a moral philosopher, I guess, would be my main area of study. So I think in terms of morality and right and wrong. As a Christian, that's what we're supposed to do. So anyway, I made this analogy, and it works, and it's now becoming well known, and I'm grateful for that. So the idea is presented. You can look at the video that comes up when you go to my channel. You'll see the main video, and you'll see the links to these diagrams and so forth. But I'll just go over briefly here. So the idea of a selfish circuit is you have a bulb, or say a motor coil, or just an inductor, in which you are closing a loop across a battery. And this is a closed loop circuit. This is where pretty much all of our circuits, and that's kind of the definition of a circuit, is a loop. But I'm going to tell you that there are, well, we get into the whole second chapter of this book is about open circuits. One-wire circuits, or even wireless, is the third chapter. But in this case, we have a closed loop. That's what you're familiar with. It's very hard to think otherwise than that. And so you have your losses in the system. So the battery represents the source of the energy, and the bulb represents the load. So we've got the plus and minus there. So what happens is the battery discharges itself when shorted. It's not that the load is actually being powered by the energy is transferring to the bulb from the battery. It's hard to not think that way, but that's not what's really happening. The energy is still coming from the environment, and the battery is discharging itself in a closed loop. Now the battery is discharging itself at the rate of the load and the losses in the line. And so you think of it as transferring the energy. But when you think of it that way, you limit yourself in what can be done. Now we talked about, in one of the last videos, Kirchhoff's law, which isn't a law at all. it's a special case of Faraday's law. So that law, supposed law, Kirchhoff's law, relates to the amount of power in any or all combined points in the closed loop will always equal out. I don't need to get into the details of that law, but it's only applying to a constant current closed loop. That means no abrupt pulses, no abrupt changes. When there is, that law is no longer a law. It's shown that it's not a law, it's only a special case to a closed loop constant current. So that's normally your electronics is run this way. So I call it a selfish circuit because it consumes the energy upon itself. It doesn't share the load. So the idea of the loving paths, now we're going to show, that was a bulb as a load. Now we're going to look at an inductor. So in this case, it's one of my motor coils here. So now we still have the closed loop, but since there's an inductor, what happens when you apply a load across an inductor? It resists it, so to speak. It takes time before it flows constantly. Once it's the initial turn on creates a disturbance, which is normally grounded out or shorted out through a snubber diode system. So there's a pulse and then there's a reaction. Well, at the moment of switch on in the circuit, there's a response, and then at the moment that you turn off the switch, there's also a response. And there's really two pulses that we are going to charge a battery with over here. But when we do this, we close this loop and close this loop, we limit the full potential that we could get from this process. If we just run a constant current, you're never going to get a gain from your supposed input here. So you're going to have your losses, maybe 50% loss or whatever you want to, say, depending on what you're doing. But anyway, I call this a selfish, unthankful circuit. And it relates to the analogy of your relationship with God. If you are receiving energy or gifts from God and you just use them for yourself, then you're selfish and you're unthankful. You're not put here to consume everything on yourself. That's the way we're brought up in the secular society today. In essence, the only real giving is to make yourself look good in the eyes of others, to get ahead. Look out for number one, care for your friends, but you're not really here to serve. You're here to get and consume. And that's the selfish circuit too. The energy just wasted upon itself. So when we go over to and this is very important to grasp. Some of you are trying to figure out this third stage process we'll get into. But until you really grasp this point, the basic level, you can't really understand that. It doesn't make sense to you. So when we compare these two, contrast them, so now this diode we've moved over and gated out to the negative. So these batteries are in series. So they say this is 12 volts and 12 volts. Now you can see the batteries are, in series with each other through here. So it's 24 volts. From here to here, it's 24 volts. So this battery is not charging this battery, even though you would think if this was switched around, then you could do that. If this was 12 volts, and this was maybe 10 volts, and the polarity was the opposite, you could charge this battery, right? That would be like an amplifier type of circuit, a battery charging circuit. But notice they're in series with each other, so it's impossible for this battery to charge this battery. If you look at the connections, I've had engineers of all types scratch their head and look at this circuit for a long time and try and reason a way around it, and they can't. So if I actually make this 300 volts, this battery can still, well, this system here can still charge this battery, even though this is 12 volts, this would be 300 volts. So it's not battery charging. This battery again is only discharging itself because it's in a closed loop with this inductor. The rate that this is closed will be the rate that it discharges itself. It's very important to think about that. Now, since we've opened up one loop here, we can have this secondary effect. Remember, there's two pulses, switch closure and switch open. So we can look at maybe here and here, pulsing into this battery. So we're looking at the inductor now. But is the energy coming from the inductor? No. And that's another whole thing. And it's not my point to get into all those details. But you want to consider the fact that this is a triggering event. So this is creating an effect. It's creating a disturbance in the ether, if you want to call it that. The local environment is getting disturbed. And it's responding because the local environment, everything in God's creation seeks to balance out, right? Seeks equilibrium, like your body is always trying to balance everything. And it has a lot of different chemical reactions to keep it all in order. So electrically speaking too, there's a balance. So when you create an imbalance, which you create with turning on, pulsing this inductor and turning it off, you're creating a big change. And the faster you do it, the more you're going to get out of it if you tap into it. So now we're taking advantage of that balancing back effect, and we're using it to our advantage. So we're sharing the load. This is the loving path, giving. So now we're not just consuming it upon ourselves, we're sharing it with another. And it may sound corny, but it works. It's an analogy everybody can understand. And it's something that actually I didn't realize, but Carlos Benitez 100 years ago did a battery swapping arrangement. So after I did this series, I realized that. So I call it the Benitez loving giving path circuit that way. So anyway, that's that. You can learn more about it on my video on the subject, and it's a 4, 5, 6 part series over the last 2 years. Now this is another arrangement. So in this case the batteries are parallel with each other, and say battery number 1 in this case, usually we have battery number 1 on the top, but that's fine. Say this is 24 volts and this is 12 volts. So yeah, you would say, okay, well that makes more sense, Rick. That's more conventional charging, and that's true. So here we have the negatives connected, and now we put a bulb across there. Now, if this is 24 volts, this is 12 volts, then there's going to be a difference of potential of 12 volts here. So the bulb, say you have a 12 volt bulb here, that will be lit. So if you have the bulb or you do not have the bulb, the same charging is going to take place here, with or without the bulb. So like I said, this is showing you, this is not an efficient system, by the way, what I'm doing here. This is not meant to show that. People have been confused by this analogy or this explanation here. And I don't want to overstate it because the pulse system is needed to do the gain. But there's a gain here in the sense that if you didn't have this bulb and you attempted to charge this battery, which is actually seen more if these were considered capacitors. So let's forget that they're batteries because the amount of energy in the second battery is going to change at how fast you're charging it. There is there's more of a loss when you try and charge faster. So that's not my point to get into. So say these are capacitors now, and this was fully charged and this was fully discharged. And you had two capacitors here. Now we're not going to talk about the losses that you have in a capacitor, but I want to simply say if you repeat the experiment like I've shown in the video, where you have a fully charged, say 24 volts capacitor here and 0 volts of the same capacitors here. Now, with or without the bulb, you're going to have the same voltage appearing in this battery. So that shows you that the bulb runs for free. Now it's not something that I want to make a big deal about, and I don't want to be misunderstood. Like there's always one guy who doesn't pay attention, skips around the video and doesn't pay attention to the details, and then starts trying to misunderstand me. Well, not trying to, but ends up misunderstanding what I'm saying. So this is, I don't want to make too much of that, but let's go on to the third point. So when we combine these two systems, so that was the first one, we're charging a battery, and then when we go and add this to that, we come up with what I call the second stage process. So this is the first basic stage, where we're charging a battery, or you could run another load. I'll show an LED being lit instead of a battery, or with the battery, or whatever loads you can. This becomes a negative resistance, right? True negative resistor. The battery is a true negative resistor in this situation. It's receiving a charge when normally there would be nothing there at all, right? So we're going to combine these two, stage one, and this is stage two. So here's the same second battery over here, and I'm going to call battery number 3. And then this is over here. Now, I had the switching on this side. Normally we do it on this side. It's not so important. So this is just an old diagram, and I could have drawn it different, but this is the way I drew it. So, never mind the bulb, because that was something that nobody really paid attention to, so never mind it. The optional bulb in the circuit. Anyway, so here now, like I said, normally we do the switching right here, and we reverse the positives on this side, negatives on that side, but doesn't matter. So anyway, now we have extended this circuit to include another battery. Well, normally it would be like that, shorted across, right? So we'll see in the next diagram. And then we're charging this battery, And these batteries, if they're pulsed the right way, could be switched around indefinitely. Like normally these are rotated back and forth, right? But now we're going to rotate these ones and have this one continually charging. Plus we still have the motor power. Like I say, if you're going to energize a coil, you might as well push a magnet. Some of you are laughing because I say that all the time. So now this is the second stage. Now, if you don't pulse this very well, you're going to run these batteries down eventually. The disadvantage of this system is that as the input battery discharges and this battery charges, the operating voltage decreases. So it's something that you'd switch more regularly to keep it more stable, because obviously with different voltages the RPM is going to go up and down and all that. Now with the Arduino we have the capability of making the circuit hold an RPM, which is nice, you know, to a certain extent. So anyway, this is the second stage process. So it's an open, these are all open paths. So this is an open loop, a floating ground. And this is as well another open path, a sharing, giving, loving path. And then we apply that further, and you can keep on applying the principle. But you have to start and understand the first principle first. So if we look at, here's another example where, say you have a solar panel. Normally you have a solar system like this, say your panels are about 22 volts on a 12 volt system. And then you charge a 12 volt battery. Nowadays they like to do like 600 volts and then convert it over so they don't have to have big lines. Anyway, so you got your charge controller. Now you don't have a motor usually, well, ever, except for my systems. So you could use this as a solar charger controller. So you're charging this battery. So now, if we want to think about it in terms of you know, here's your FET, and in this case I'm just running a basic trigger coil circuit for illustration purposes. So now what's happening is, so I have here the inverter that you'd have across your battery, right? So now you're still charging this battery, but now we've got the inductance here, and now we're charging, in this case we're charging a capacitor and an SCR. I'm going to show that here today. That's another thing I'm going to show, this charging a battery. The generator coil output here. And that's separate from this illustration, so we'll get to that in a minute. So now we're charging up another battery bank while we're having mechanical load and still charging our solar batteries, pretty much like we were if we didn't have the whole system. Again, you might as well, if you're going to charge your solar batteries, you might as well run a motor, and then you might as well charge another battery too. And so at night you can use this battery for your input. If you got solar panels, you might as well use them. And I know I have these solar panels that I've never used for years, so I should talk. So anyway, we'll get into this particular part of the circuit. This wasn't really in relation to what I was trying to say, but this is a fuller diagram. We can use an SCR to charge a capacitor and pulse it into the battery, and that's what we're going to do. And that is great because we can regulate the rate of the battery charging with the size of the capacitor and so forth. So that is the combined second stage process. application. Now we're going to look at, so that was over here. Now we're going to look at stage 4. So now we have, again, the second stage here. You know, the first stage is right here. The second stage there. And now the third stage is adding another open path. You can see it's across the one wire. Now on this side it's the negative side. Usually we do this positive side or both. So now we have a process here, and I'm going to show that today. It's right here. As I've shown in my conventions the last 2 years, just the basic, it's not 0 voltage in my case here, what I'm going to show, but it is just opening the loop again. And now we're charging another battery. Now, if you don't have this ideally arranged or set up, then this battery doesn't charge as much. And if you have this in resonance, and you have a high Q, which is the quality factor, it's the amplification gain that you get in resonance. So these coils at about the frequency we're running at are about 100 times gain, 100 Q, rated with my LCR meter somewhere around here. The LCR meter shows at 100 kilohertz a Q of almost 100. So it's optimum. Well, I didn't even check the actual optimum frequency of the system, but we run it at about 1.2 megahertz. So it's around 100 Q. So that's 100 times gain from your input. So that's pretty good. Here we're talking about two times the gain. We're charging one battery and we're running one mechanical load for one input. And that's pretty impressive, but here we have 100 times the gain. Now we're only running at a very low voltage level, although with 9 volts input, I got around 1,000 volts output. So it's kind of, you gotta be careful with that. I try to make it as safe as possible with the lowest voltage you could run. So I made another coil that will probably do a second enlarged kit with, for those who have already ordered this kit. We'll get into that in the future. So I made another coil that was quite a bit bigger, that was 250 times the gain. So we had about 4,000 watts, or 4,000 volts on it. Well, 5,000 actually, I think. Anyway, we'll talk about that in the future, Lord willing. And so anyway, that's the Q. So depending on how much in resonance this system is over here, and the tuning of the motor, we can do with this process, we can multiply the energy out again and again and again. You know, hundreds of times the output, or millions, or infinite, as long as you keep adding to the process. So this stage 3 isn't really, there's really nothing beyond stage 3 because it's open-ended. It's showing you, you know, this whole idea, which I get into, the whole concept of the multi-body. Like I talked about, the main thing about this kit isn't so much resonance, is the whole concept of the multi-body. So when we have the selfish circuit, we have one body, one system, that's one loop. But when we open the loop up, it becomes a this is a floating ground multi-body So this becomes yet another branch off of it. So then what we can get into is, like I talked about in this book, the phase conjugate mirror effect, where we can send the energy back to the input, both to the motor and to the battery, so that you can either keep them in a state of charging or zero, no in or out, maintaining voltage. And that's what we showed at our meetings the last couple of years, 3 years now I guess we've been showing that, where the battery stays the same. It holds its voltage. And it's actually harder to do that than to charge it or to have it discharged, to keep it right. You have to really tune it all. And that's one reason why I haven't shown this until now. I'm kind of showing this. I did show it a little bit here and there in previous videos, but I didn't really want to get into that because people would destroy their circuits. Now we can actually incorporate, because I've got a big capacitor here across the MOSFET, across the switching. So that energy that's being sent back into the circuit, we can absorb it so that it doesn't destroy the MOSFET. So that was one reason I didn't really want to show that to everybody, because I knew people would try it and they would blow out their circuit or partially blow it out. And then, you know, it's not for, if you don't understand it from what I'm saying, then it's not for you. Once you understand the process by experience, then you can start playing around with it. But if you don't, you're in danger of blowing out your parts, melting down your coils. And believe me, those are melted down coils there, because I was foolish enough to use that with experimentation. And I didn't have the circuit breaker, which I have on here, on there, and I had 100 amps flowing through those coils and they melted down. It's going to take me a couple of hours to try and replace those coils now, because they're all carefully spaced and all that, glued down. So anyway, you also can blow out your FET, or you can partially blow out your FET or transistor, MOSFET. And so I didn't really want to get into that. So there's a lot of potential here, and you know, it takes some advanced knowledge to understand how to balance it all out. Like I said, phasing, phase conjugate mirror. So you're phasing the flows of energy, and again you're creating another gain here. So it's not just a series load like this, it's also a multiplier. So we could actually add this again and again, like I showed my little black box, wherever it is, I have no idea, where you flip the switches, click, 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 and you're adding 1, 2, 3, 4, 5, 6 of the same process. And you have 6 different loads. And then this battery could remain the same charging rate if you do it all right. Anyway, that's that. Don't need to get into that anymore. I've covered that. So now let's get into what we're here for primarily is the various models here. I've got 4 different models, and well, there's variations within the single model. So the difference between this one and this one will be a double stack, but I'm showing it, there's double spacers inside here. So let's talk about this motor. So there's 2 different ways of making this motor run. One with the single space between the rotor and the coils, and one with the double space. And then there'll be 2 different options, 12 and 24 volts. That's the option I'm selling right now. Everyone who's ordered is going to get the 12 24 volt module. If you want to do 36 48 volts, we have to have a different code, because I tried to make it all in one. I mean, there's not going to be any change to the motor, but I have to have a change of code, and I have to actually beef up the parts a bit more for the 3648 volt model. So that will be the next focus for what we're doing right now. So so there's really some options here. You've got the 1224 or 3648 volt difference, and then you also have the single or double spacers here. So what this motor is, it has 4 motor coils, and we're going to put them on each corner, and then 4 generator coils, which are going to be on each side, the center. So right now, what I've done, if I assemble this for you, this is going to go to the first customer actually. Once I'm finished this video, it's going to be shipped out. So anyway, this one also, is the update on this is that we have 8 magnets rather than the 4 magnets per rotor, and that made a difference, so that we could have the generator effect, the particular effect where it speeds up the motor when it's shorted. We're going to get into that in a minute too. So you have 4 motor coils and 4 generator coils. Again, these are the coils. Now, for those who are wanting to understand how to assemble this, the rotors come assembled and the circuit board with the wires are all assembled. And all you have to do is put the mechanical parts together, and I have diagrams showing that, and this video is going to be showing you the details now. So there's some writing on the bottom of these coils, and we're going to place that on the bottom. So this fits into the plate. You want to put the feet on these 4 rods here, and I show one already connected, so you can just copy that when you get the kit. And then you want to take a look here at the spacing, how high up you want it, whether you want any of these rods to stick up higher. And then what you do is you put the legs on all 4 of the bottom plate. Now the bottom plate, it's important that the flange of the bearing is, let me show that. The flange of the bearing is down on the outside and it goes up on the top. So now I already glue these in with epoxy. One's got dust on them. So this is important because there is a flange here. You can see sticking out here, and that has to go on the bottom because really we're attaching the rotors on the side, and it's clamping in. It's holding the bearing in. So you don't want the flange on the inside. So that's the bottom, and then the top is going to have the flange going up. Very important, and sometimes I've made that mistake and had to take it all apart again. So that's what you want there. And so once you place the coils now, so what I do is I place all of them around, and I put the generator coils facing inward. And I just go like this. The bottom wire going off to this side, the top wire coming down that side. And I place them all the way around for the generator coils inward. The motor coils on the other way, I face outward. And I put them on the angle, oops, not like that, but like that. so the lines, the laminations are in line with the magnets. And then I place them out like that, because what I want to do, as you can see these wires, I have 4 equal length wires. These are perfectly wound coils. They're all exactly the same, exact same inductance. So this is the first time we're really doing that. We're really trying to get these all exactly the same. So you can see it's a little bit of a mess of a wires here because we're having all the wires the same length. Because I don't want a shorter length of wire for these coils and longer over here. So anyway, we place these and then we'll attach the wires that are included. So I put the black wire on the bottom, the red wire on the top. The black wire is going to go to the center terminal of the MOSFET, or this red wire that will already be, the black wire is going to go to the black wire, the bigger black wire. So all 4 black wires from each coil are going to come to the big black wire, and all 4 of the red wires from this motor coil are going to go to the big red wire, which is going to the positive primary battery. So now I'm showing these batteries so that you can see the voltage on the batteries. The reason for that is that, as I've explained time and time again, as you can see where the batteries are at. So this is going to be the run battery. It's sitting at 13 volts. That's pretty good for a battery. And that's not a sulfated battery, so that's where our Renaissance batteries sit. This is a charging battery, and that's a charging battery, although that one, I'll admit, is not very high capacity. There's a free battery that I got, an electric wheelchair, and so it's going to charge a lot faster than, these are all good batteries. I just grabbed that. It's not important to show the rate of charge on there, but I want to be honest with that. Anyway, I show those battery voltages so that you can see I didn't just run a load and then the voltages, like before I started the video, you can see the voltages are stable. So anyway, going back to this, so you place these in the bottom of the frame, and then what I do, before I put the top plate on, I connect the generator coils in series with each other. And then the final 2 ends I bring out here, and this one is going to a power cord that's going to plug into this variac. So again, the generator coils are completely isolated from the motor coils. They're not electrically connected. So this is induction, and it's electrostatic induction that we're dealing with. So I want to talk about that like I did in the other video pertaining to that motor. So now what happens is, then you put, once you solder these on the inner, you don't have to add any wires. That's why I do it this way. I solder them together. So the top of this coil is going to go down across right in front of that motor coil, and then you solder it together. And then you come out here. The bottom of one coil and the top of the other coil will come out. And I use red and black wires because that's what I have. Should probably use a different color because it's not positive and negative. This is AC output, and that's what we're going to talk about going into this variac. But let's go on from here. So the motor coils connected. Then we put the top plate on. Don't forget to put, like you've already mounted each leg with the nuts and washers on there. So each foot gets a nut, lock washer, regular washer, and then a nut on the bottom. And you can see I had to screw it down the way. When you get the kit, you'll understand, because you'll already have one example of this. So now you've connected all 4 plates up to the legs, and make sure they're the same length, the same distance, because otherwise you'll get this wobble, right? You want it balanced. But don't forget to add another nut and washer, and put them about halfway down or so. Then you put the top plate on, and then you pinch these together, more or less, but equally on each side, and you put the lock washer and top nut on each one of them. And you should have a little bit of space so that you can mount this. What I'm doing now is mounting the hull with a loom, and I have a 12 gauge wire that I'm using to bend and to hold the wires in place with a heat shrink tube. And then the hull switch faces down. The face of it faces down. So I'll have all that already for everybody. So I'm assembling quite a bit for the unassembled kits in this already. So it's almost plug and play. So anyway, you put those plates down, you put the plate down, make sure the top flange faces up, and then you pinch it down, and then tighten the bottom nut there. Take 2 9mm wrenches so you can really get it tight, because there is a little bit of vibration in this motor, and we did mostly solve that, and I'll talk about that in a minute. So anyway, then once it's all tight and they're all equal, now these rods aren't exactly the same height, so but you want to measure the distances between the ground and the bottom of each plate so they're all equal. And then this might be a little bit different on the top, but you want a little bit, enough so that you can put this loom down here. So I've got maybe 3/8 of an inch, what you need, so I can put the loom on, then another nut. So then what happens is you glue it down with hot melt glue. Open window, please. Don't breathe it in. Hot melt both sides. Doesn't take long to dry. Don't put it too high, because if you have only one layer, in this case, I'm actually touching. I can see it. So a little bit too much glue on this one, I'll have to cut it off. If it's rubbing, then it's gonna put a big drag on the motor. So this one, you can see it's slightly touching. I didn't see that till now. So you want to give it a visual. If you're double spacing it, then that won't matter too much. So then you're ready to put your rotor together. Now, the thing about it is, let's see, let me pull out a rotor here and a shaft to show you. So you have so this is the last of the 4 magnet system. So you can see here now, well, let me hold this carefully, or put my hand up so that it can focus in on it. Oh, sorry. So you can see I have filed down just 1 quarter. So you can see these flats, and then you can see that I've already had the set screws. You can see the circles, and then I've done the same thing down here. So this was a shaft I was using. So you take a file and got a file here somewhere. But anyway, you file this down. First you want to do the bottom one. And this is kind of hard to do because you got to get it, you want to get it completely, you know. What you can do is put the rotor in once you do one flat, and then tighten the set screw down on the area where you're going to do the next one. Not too tight, just enough to score it. And then you can draw a line further than that little mark that it will leave once you pull it out. And then what you can do is you just file on there, you know, you just kind of measure how far up you want to go. And then if you don't want, like, this, the reason why I don't file these for people is because they may want to have the shaft extending beyond the bottom. Like they want to maybe put some kind of mechanical load on the bottom instead, and I don't want to do that for people. Anyway, so you have to file your own. If you don't file, you don't have to file so much, but I've made these. Okay, so here's how it works. And this is why I'm so late on shipping these, because these rotors were not balanced. When I took out the holes for the set screws, I ended up having an unbalanced rotor. So there was some vibration. I mean, if you load this thing down, you won't see it as much, but once you get up some RPM, it really feels it. So I have these aluminum lugs, which I create slots in, and they'll go right to the edge. Now, if you don't put the flats on, these will stick out a little bit, and that's not too big of a deal. I do file them down so that they're not sharp or anything. But anyway, the particular set screws that I have are rated so that the length of the set screw will go to a flat. You know, it doesn't have to be very deep flat, but just enough. But if there is no flat, this will be screwed in and it will stick out a little bit because it will butt up against the end of the set screw. Now, I'll probably do them the same size in the near future, but for now they're different sizes. But anyway, that's what happens there. And you'll see it's pretty balanced. I do have a little rubber foam on there, and that eliminates the vibration pretty much. So you won't feel any vibration in your house shaking like it's going to fall apart. So that's one reason to get rid of my other videos, is because there was a lot more vibration, and that's kind of embarrassing. So so that's important. You file the flats down, then you put the spacer in. You tighten it first, of course, with the Allen wrench. I provide one with the kit for you European people that, or other non-American, rest of the world. You don't have to find the right Allen key, I provide it. So then what happens is you put the spacers that you want, one or two, and then you put it in, and then it will hold itself in place. There'll be a magnetic lock like you feel here. And then what you want to do is figure out, what I do is the opposite side, the opposite corners, I place the top rotor so it's more, the slight imbalance here will kind of balance itself out when I do it the opposite side. So then I decide where the flats are going to be and do the same thing. And put my spacers in first, And that's that. Then I mount this Hall, and we've decided pretty much top dead center or a little bit after top dead center is where you want to put it. And this gives you the ability to bend it and place it where you want. So I'm just under a 1/4 inch between the top of the motor coil here. Now we can't do it, there's not really any space to put it on the plate anymore. So we're bending it above the plate. We're bending it so that it's above the plate. And then what happens is I'm in not more than, a 1/4 inch to the end of the Hall from the edge. So what happens is the magnets are really powerful. They're 1/2 inch by 1/2 inch rounds, and they pull 28 pounds of force. So the magnetic field is pretty big, and that's the disadvantage of this smaller rotor arrangement with that many magnets, is the fields overlap. It's especially noticeable on the double stack because the magnetism is doubled, right? It really feels it. And anyway, so that's where it wants to be. And we have a limiting effect in the circuit board. And there's a potentiometer here, a variable resistor, that you can adjust the on time. So the Hall senses where, I'll get into that I guess when we start up the motor. But when we turn the pot, I think it's about 50% on time, or 45 to 50%, somewhere around there, I have to look, on time at full throttle. So when the pot is turned all the way to the right, it's fully on. So when we back off, we lessen that percentage. It's a bit of a trick to do because we have to also consider RPM. So as it speeds up, it kind of changes. So we had to adjust to that. That's why it's taken so long for me to get these kits out too, because we're trying to optimize that and limit the current so that at any particular time it doesn't exceed 20 amps. So around 20 amps, I think it shuts off. It just turns off, because I'm going to recommend a 20 amp circuit breaker that's not a fast circuit breaker like a GFI in your outdoor outlets or kitchen or bathroom outlets where there's a fast switching circuit breaker. We want a slow switching circuit breaker that can handle the pulse, but not, if something got shorted here, it would trip before the coils would melt down. That's what you want. So something that takes about 1 second to respond. So you have 20 amps over 1 second, and the circuit breaker trips, rather than you just have a pulse of 20 amps like a GFI. You ever try and cut your lawn with an electric lawnmower? Yeah, I have one. I don't use it for years, but try and run a motor on a GFI and they usually trip on you. You can't even get it going. So anyway, that's that. About top dead center. Before you mount it, you can hold it with your hand and see, but it's kind of hard. So you gotta kind of give it. This is not self-starting anymore. We tried to do that, but because of the magnetic lock is really tight. Now we could make the other one self-start with the double spacer, but it's less torque. So it's kind of a trade-off. Now the big motors, I've got the big motor here, I showed that last video. That will self-start, but these little ones don't, unless you do the double spacing. And then you have to place the hull farther to after top dead center. So that's not really that ideal. So anyway, what we have then is you just have, like I said, you soldered your wires, placed your coils, glued them down, mounted your hull. Like I said, I put this on the foam sheet, and you're ready to go. So let's look at the details now. What we have then, like I said, we're charging a battery. The thicker wire, 14 gauge wire, is going to the charging battery, and that's represented in the lower voltage meter there. And then we have, these are 35 amp hour batteries, AGM. Don't recommend AGM, but it is what I have here. True deep cycle lead acid batteries with open flooded cells so that you can add water to them is what you want, because you're going to have off-gassing no matter what. Even if they're sealed, they still off-gas. Now I'm running these are the appropriate size batteries for this model. You could get away with smaller ones if you don't want to spend the money, but we're going to be pulling, on average 4 amps, 5 amps out of these. If we're loading it down, we're going to show the generator hookup. We're going to load it down to maybe 8 amps. And then that would need a bigger battery to properly run, like over time. So then we have a little battery here, and this is bigger than it needs to be, but it's just one that I have here. So this is running the Adreno. It takes very little. It's the gate driver and the Adreno. It doesn't take a lot of power, but we need to isolate that from the main battery, because it only can do 12 volts. And if we go up to higher voltage here, and it's very sensitive, the gate driver is very sensitive to any kind of pulsing, which we have on the input battery about 40 volts, even with this big capacitor on here. So this capacitor is a high voltage 900 volt capacitor, and it's across the MOSFET, and that energy is cycled around, which is normally wasted. It's cycled around in the system. We're going to see it with this oscilloscope in a minute. So we have 2 extra batteries here that we'll use for 24 volts in a minute, and then, like I said, we have this output. So let's talk about this a little bit, reviewing. So we have the generator coils in series, and the wire coming out here, going around and around and around, very long wire. And it shouldn't be long, but it's just what I grabbed, And this is plugging backwards into this variac. This is a variable voltage regulator, it's called, but it's a variable transformer. They're isolated from each other. It's an isolation transformer. I believe it's isolation, but anyway, it is allowing you to go from 0 volts to 130 volts. Normally with an AC input, 110. Oh yeah, for you guys who are overseas. This is a 110 Variac, not a 220. And you cannot use this with 220. But if you're going to buy this, it's only going to be for the kit, no doubt. But it is a useful tool to have otherwise for 110 circuit. So we're going to run it backwards. I can't recommend you doing this because it's not the way the product was made for. And I'm making this available to use at your own risk if you're a qualified engineer. The problem with this is I already did make a mistake by doing this. Plugging this into the wall. You got to plug, you think, oh well, I can plug it into the wall. So it's not the right ports. It should be changed around to a different connector. This is the way I have it here. I'm not going to sell it recommending this, so I want you to be clear on that, because it's somebody can make a mistake and we can't really encourage that, can we? So normally you plug in this wire to the wall and you can vary the voltage output here, but we're going to run it backwards here because we need to do that for this way, for this system. So let's talk about the generator coils first. So the generator coils, as I shared in the last video with the one that has the picture of this video, or with this model here, what I said was about 20% of the energy received in these coils is coming from the motor pulse. Now I showed in that video when I turned the switch on, we had a little magnet 18 inches away that moved when I pulsed it. Right? When I turned it on, this little magnet moved all the way over there. So there's an EMP effect, electromagnetic pulse, every time the motor turns on and turns off. Boom, boom. So these generator coils, and this is what I've known for a long time, and this is why I included them in this way, right beside the motor coils. They're not that close, so this is not a shared, the laminations are not shared, the core is not shared, so it's not like your regular transformer. This is electrostatic effect. When I talk about that, Tesla talked about that, and I have that quoted in that book there from Tesla. The electrostatic effect. So now what happens is that receives some of the energy. The total energy is from the electrostatic, from the motor coils. And then maybe 80% of the energy, when you're fully loading down the coils, you know, this output here, is from the magnets passing the cores in each of these. So every time the magnet passes, you know, you have your regular generator action there. So this is why when you short the coils, so if I short this, which we'll see in a minute, the motor will speed up. Because what I'm doing is I can't really get into the details of what's happening, but the point is because of that electrostatic effect, when I short out the coils, the motor speeds up. So we're not talking about the generator effect from the generator coils. And so what we'll see is, so if I put this at 0, so there's a primary and a secondary, and we've just reversed them. The primary of a transformer is where you have your input, and the secondary is the output. But here we're reversing that. And so what's happening is, we'll still call it, the primary now is the secondary is now the primary. So we'll call our secondary the reverse secondary, shorted. And so this still will speed up the motor. And then, as we increase the voltage on there, now with it turned on, connected to our loads, the motor will start to slow down the more we increase that. Once we get to a certain point, so we'll still, within a certain low range here, low voltage range, every time we turn off the switch, the motor will still speed up, because it's still better to run that load in a kind of shorted coil condition than it is to leave this open, which makes you scratch your head to figure out exactly what's going on there and why that's happening. So it's a very interesting phenomenon. I've always included it in these motor kits from the earliest one, the first 3-pole monopole I did that with. So now, once we get to the point where it's maybe 25 volts or 40 volts, depending on the RPM and the particular setup here, when we flip the switch, it will be equal. So we're going to show that in a minute. But then after that point, the voltage gets higher and higher, and the motor, when we flip it off, the motor will start to speed up, because now we are entering into the generator mode, where we're taking the energy from the generator coil more. I'm just kind of being simplistic here. So in the last videos, we were showing just the output to a capacitive load, which this LED with the capacitor worked really well, works the best. So now we're going to show resistive load and another capacitor load with the battery. So that again will work really well. And I did show the battery being directly charged from a bridge last time, but this time we'll show it through the cap pulsar, the SCR pulsar. And then I'll also show 3 incandescent bulbs here. Yeah, I went out and bought these the other day. I felt like a fool buying incandescent bulbs, but it's for the video. So anyway, this is going to show you the difference between a resistive load on this output and a capacitive load. And there is a big difference. But some people will only consider resistive loads. They'll only think that's the true test of a system, if it can handle a resistive load. And that's not true, that's not fair, because if it takes so much energy, if it takes 100 watts to power this at full brightness, this 100 watt LED module, then it takes 100 watts, you know. And if I run it using this system for less wattage, then what does it really matter? You know what I mean? We don't have to limit ourselves to resistive loads. We don't actually need, we can run this into a battery and run an inverter off of it and then do our resistive load, although the inverters are not very efficient. So anyway, this is just showing you directly to a resistive load. And the thing that we're doing here, we'll show that after we do the battery, is that these are in series, because the voltage gets up there to 350 volts or something like that on this output. So what we, actually not this output, but the output here when we step it up with the transformer. So what happens is, because the voltage is higher, we have to match it all, because we don't want to run a higher voltage in the bulbs or higher amperage. So I've got 3 equal bulbs here that we can run, and they're going to light up to pretty much, well, a decent brightness anyway. So I'd rather go under than over. So that's the point, is these are for 110 volts. So the filament is made for that voltage. So if we have a higher voltage, we want to, these are in series with each other, they're not in parallel. So that's what I'm trying to explain there, is that we've matched, we can go down to 2 bulbs. I think we'll go down to 2 bulbs with this arrangement. This is more for the 24 volt model, for that wattage of bulbs. Now, let me say this. The output from these generator coils, considering the input in the motor from this primary battery, and again, it's not electrically coupled, it's the mechanical load that we're taking off of that, and it's an inductive coupling, like I said. So what happens is we get about half the power with a resistive load. So if I'm running 60 watts and we've got 30 watts of bulbs here, these bulbs will run at about 30 watts worth of light, you know, so say full brightness at 30 watts, and then we've got 60 watts running power, you know, so many amps at so many volts. But if we go over to the capacitive load, well, the one limitation is, well, let me finish that thought. If we go over to the capacitive load, then we can get much more out of this system. So it's more like the same amount from that. And that's where my video, I wanted to correct my previous video, because I didn't want to, I was kind of vague about what kind of output. I know I did say capacitive load, and I showed the LED, but I didn't want to give the false impression. That's why I'm redoing this video step by step, very carefully. I don't want to oversell this variac, because if you're going to do a resistive load like that, you're going to see there isn't very much, after you get to that sweet spot on the variac, turning it any further is just going to increase the voltage and lower the amperage. So it's not, if you want to use the same bulbs, then you're limited with the variac, what you can do. Whereas if the capacitive loads, you're going to see as I change this, we have the full range of the variac at our disposal. So I'll talk about that more specifically once I get this running here and show you that. So let me get it started now, I think. And I'm going to start this off with it not loaded, so we can short that out and see the difference. So I think we'll start focusing on this first. Oh, one more thing. Now I showed this, and I won't show this running because it's all, this one right here running because it's, the coils were melted down. So I can't do that. Unfortunately, that if I delete the other video, you won't get a chance to see that running at this time. So what I was going to say about that motor, so there is 12 more coils wrapped around the motor coils on that setup. So there's 20 coils there. So there's an inner row of coils. So there's 4 more coils on the inside behind each motor coil. In that case, I've positioned the motor coils this on this side in order to be able to wrap those coils around. Otherwise, if I had them here, this would be in the way. So I have a motor coil on the inside of each, or sorry, another extra coil on the inside. And then I've got two on the outside, as you can see clearly. Now, in the previous video I showed the outer 8 coils in series with each other, and they were running a 10 watt LED. And then I showed the inner coils running another 10 watt LED, and they were isolated from the regular generator coils. Now those were not receiving any power from the magnets. The only thing they could have been receiving from the magnets is indirectly from the motor coil. And that's not very much. But what was happening is, and you could see when I turned on the motor that there would be, the lights would flicker before the rotation of the rotor. So this is again electrostatic phenomena. And the thing is, you can wrap as many coils as you can get around there, and they'll be additive. Now it's not a lot of energy, but it's extra. So, like I said, 20% of the generator coil's power was coming from that effect. So I just added 3 more coils per motor coil, and I increased that. And it didn't change the RPM. The motor still functioned exactly the same way. It didn't have any negative effect upon the motor action and the battery charging into the charging batteries. So if I had wrapped the wire, an extra wire like a bifilar coil, it would have been different. For those of you who were around, 13, 14 years ago when we were doing all these various bifilar coils and all that, you would see that, you'd remember that if you had the third winding, you had the trigger coil, you had the motor coil, and then you had the secondary winding. If you tried to use the secondary as an output as well as the regular output, it wouldn't work because you have a transformer action there. So we're not doing a transformer action by adding those coils in front and behind. We're having an electrostatic phenomena. So this has everything to do with the kit and what we're showing with the coils. And so you can think about that and everything I just said in the last couple minutes, and some of you will be nodding your head like, now I get what he was trying to say. But I'm kind of leaving that open-ended for you to figure some things out. Just listen to what I said, pay attention to those details, and that should open up a big door for you. A very big door. So anyways, not a lot of extra energy there, but consider that. Consider this like a radio, like a crystal radio, like I've shown. This is the receiver, right? But near field, right? All right, so that's that. Let's get going on this. Let's run this. Let's turn on our voltmeters again and make sure we can look at the voltages. That one, like, it's kind of odd because it seemed to have charged. Anyway, let's consider, now this voltmeter right here is the AC coming out of this. It's not terribly important. It might not be connected properly there. Oh no, it is. So we'll look at that voltage a little bit, in relation to the final voltage in this battery. So we're going to start off at 0. Well, this is not connected yet because I have it disconnected here. We're going to short this. I've got my tachometer here, so we can check the RPMs here. And then we've got an ammeter here. So I'm going to leave that like that. It should be able to be seen, I think. Yeah. Alright, so let's get this thing started. So like I said, let me, for reference, 1242 is the charging battery, 1302 or whatever it is the input. So yeah, it's fully charged battery right now, and this one is somewhat discharged. So let's get it going. Oh wait, gotta hook it up. It goes tick. So what we have here is it's going to draw some more amps. Now we're at just about 4 amps. And I don't recommend starting it at full blast at the beginning. So yeah, now it's 395, so it's about 4 amps exactly. And we can see now that's undercharged, 1260. It is charging that battery. So relatively 1-to-1. You know, you can have a bigger battery bank and get more out of it. You could charge 24 volts. And you could actually charge less too. So let's see what happens now. Okay, we got RPM wise. We've got $3,500 RPM, well 3,570. So you can see there's hardly any vibration. On this table I feel no vibration because there isn't very much vibration on here either. So now we've shorted it out and now it's really speeding up. Now there's a little vibration here. So now it's now we're never going to run it like this because it's not doing any work. I just wanted to show the RPM. So it's about 4,200 RPM, still climbing a little bit. So now we're going to not short it anymore. It's going to go back down. So now I'm going to plug this in. Now this is already turned off and it's turned down. I gotta move this hall just in the right spot. So now what we're gonna do, hold on. So now, if we look at this battery, see now it's at 0, it's not doing anything. Once we start turning it, you can see the voltage, the AC voltage. And now we're starting to charge that battery. 12.2, 22. So now the battery can hear, or the motor's starting to slow down. So that's the AC voltage across the cap. And then the SCR is switching it with a diode right here. So in this case now, I can have the full, I can put a full load on this. So we're at 4 amps still. I can keep turning this voltage up higher and higher, and you can see it getting higher here. and you can see that battery is going to charge more and more. And this is still holding at 4 amps, right? It's just a lower RPM. And that's where you're going to really run this motor. You know, it's still quite high RPM. Right now we're at 3,200. Oh wait. Yeah, 3,200. So let's keep turning this. Like I said, this is not a very good battery, so it's going to go up pretty high. I don't want to mislead people and think that's as good a battery as that one. I should have probably just used one of those initially. And so you can see the voltage here now, just giving you an idea. So now we're all the way up to the max at the 130 volt setting on this one. So it's 16 volts across that. That's a 10,000 microfarad photo flash capacitor. They're about $30 to $60 depending on where you get them. Probably could pay $200 for that somewhere, but so anyway, that's that one load. And so now we're drawing a little bit more amps on this side, but we still have a good bit of torque here that we can use, and we're going to run, when we're done this experiment, we're going to hook it up to the other, to the generator and run this with this at the same time. So now we're going to go back to 0, and we're going to hook in another type of load. Oh wait, sorry, not that load. Let me turn this off. And then what we're going to do, so I'll leave that hooked up and we can see where the voltages come to. Nevertheless, it does charge the batteries fairly well. So it represents, like I said, a capacitive load rather than a resistive load. Now we're going to run a resistive load. Alright, so now I've got these bulbs hooked up. Now, this is for the bigger one, so we got a whole bunch of bulbs here to play around with. And I'm going to use these ones next. Actually, we'll start with those ones actually. Yeah. So we have here these ones are 7.5 watt bulbs. Now again, we're only at so much wattage here, 4 amps at whatever the operating voltage is there. It's going to be 70 or something, I can't tell until I walk around. Okay, so like I said, this is resistive load, so this is going to be about half. Now I have to be careful that I don't exceed the power here. These are a little underrated. So anyway, let's get it started again and watch. Oh Oh yeah, so it's under load, well, say 12.5. Now let's turn this on. Oops, yeah, turn it on. Remember, these are very low wattage bulbs, so we don't want to put them, we don't want to run them too hard. So if I go up too high, they start to flicker. See, there's only so much point. So when I go to higher voltage, they don't want to run. So now they're at like full brightness. And you can see the voltage across them is 200 volts. So it's too high, really. So now we're at 180 volts. Remember, this is just resistive load. It's a lot more delicate matter. So now we're actually more at 150 volts. This is AC, remember. Remember, this is higher frequency. Oh, and I should be looking at the oscilloscope. So we can see the frequency. So there's the waveform. So you can see it dips down. You got the H wave split in two. So that's the capacitor filling and dumping. And we can get various ripples because the coils are in resonance a little bit. And so they're oscillating. So anyway, that's that load. And if we change the bulbs now, so you notice now the motor speeds down. It's like turning the switch off. So that's what I was talking about, because we're at that lower setting. And then what I'll do, I should really only have 2 bulbs in this arrangement. Oh, I got this thing backwards. So anyway, when we turn this back on, see, I can only get so much voltage and power out of it because it's not rated. So now if I bypass one of them, of course these aren't the proper wires, these are these cheap Harbor Freight wires. So now I can get more of the brightness. These are 11 watt bulbs, so they're not much more. They're more decorative bulbs. But I'm just trying to show the limitation of the resistive loads and of incandescent bulbs, which are really heat lamps. These will get hot, not too hot, but so you can see the dipping now, depending on my RPM. Just checking the heat on these setups. So you can see how it kind of dips. These meters time out on it. So anyway, that shows you if I go up, there's a sweet spot, so there's more where it wants to be. If I go too high, it's no good. too much voltage or too little voltage actually on the other way. It needs so that's about the sweet spot. So that represents, you know, your 30 watts of resistive power, and that's you know, your 60 watts or so input, 30 watts output for resistive power. Now that's not including, see, I can still load this down, which we'll do with that generator coil. So now what we want to do is change it up again to the LED, which is going back to a capacitive load again. So we've got this adapter here that I'm just using. So we're going to turn this down to 0, and then even with very little we get quite a bit of light. And it doesn't really load down the system very much. So I can only go so far before this thing gets too hot. I already blew out one of them. So now we're at that equal point, right around 30 volts in this case, where it doesn't make any difference. Oops. We got to make sure we can still see the voltages on all these. So now, like I said, it doesn't make a difference. Now this one's not connected anymore, so turn that off. It doesn't make any difference now whether I have that on or off. It's a pretty bright light right now. I'm going to say that's pretty much matching the input voltage. So this is definitely not 100% brightness. Let's say it's 60%, so we're at 60 watts worth of LED perhaps. See, after a while it's just too much for it too. And it starts, once it starts blinking like that, it's too much for it, it's starting to damage it. Now I can't see. So anyway, that's that. We'll leave that on. And now what we want to do, so you can see it's still running off the generator. Right? Still running off of the generator, and until it stops. Now what we're going to do is run this third stage process, which I should probably have a different name for it than that. It's kind of funny sounding. So here we have, it's going to be a very bright LED here. Now we can look at the charging rate is going to change. So now I'm going to put the process in series. You got to be really careful that you have a good connection here. So I'm going to put the voltmeter back. Let's look at those voltages a little bit. So the charging battery has charged up somewhat. The input battery is going to come back. That's supposed to be fully charged at 12.6, right? But it's 12.7. 77 is going to go back up. But anyway, let's look at this. Now, what's going to happen is I'm not going to charge as fast. This battery is not going to charge as much because this is not an optimal system. This is a very basic method of doing this process. And yeah, this is a very special part here from China. It was from an inverter that I got that was just an absolute monster of a mess from China some years ago, and I just salvaged some parts out of it. So nothing incredibly special there. But I'm not going to get into all the specifics of that because we're going to make a product, but it all has to be tuned just right to do it right. So anyway, this is just the basic model of it. Now you'll notice when I connect this up, it flashes. So there's that infamous pulse when it connects up. So there's no rotation there. This is not, you're not charging this battery because the magnets are passing like the generator coil. This is not at all, there's very little energy from that. Well, there's more now that these magnets are stronger, but you can see there's no, that will happen without the rotor. So now what's going to happen is this is going to be a very blinding effect here. I'm going to turn off the lights so we can see this. And it's daytime, so it's still not that dark, but so let's start it up now and see if the LED is still good. So I ran the other LED even though it was on a heat sink beyond, it actually was at 170 degrees Fahrenheit, so it started damaging it, so I replaced it with another one. So we've got these two different lights. This one is very, very bright. That's at full brightness. So that is showing you that there's a lot more power going into the battery than what you can get out of it. So the output, this is in series with the charging battery. So again, I could turn this down and speed this up. But once it starts flickering, I have a capacitance across it. And once it starts flickering, it's going beyond its capabilities. Now you can see the spike on here. I have to go down in voltage. So now we're operating at 75 volts peak to peak. Now without this capacitor on here on the circuit board, you would have this voltage spike would be up there in the thousands. So that is a big enough capacitor to absorb the pulse, but you can see how it translates. Now the waveform is quite a bit different. But you see you have a much higher volt. You've got double. Before it was like 40 volts. Well, 30 something. And this is doubling it. So you've got more energy coming back into the motor. And see where you place this ammeter now is going to change. So we have .62 amps there, and again it's going back and forth. But if we go down here, we're showing 4.32. Like I said, we're pulsing this. This is getting really hot, so I gotta watch that it doesn't burn out. And again, I could turn this. See how it goes down? See, this is also a good method to judge your charging rate that you'd be getting in a battery. So I've used this process for many years now to judge, instead of having to look at a battery over time, measuring the voltages and all that, I can judge it by this response here. Now, if you're not familiar with it, you can't do that, really. So let's try and look at this ammeter again. As I turn this, so he's not drawing really any more energy here till I bottom out the RPM. So what are we looking at for charging rate? 1271. So it's kind of holding the charge. Let me plug in the lights again. So anyway, that's showing you, 3.5 amps. So that charging rate is holding. So let's turn it off for a second. And we're looking at 3.5 amps times, what is it, 12.5. So we're looking at 44 watts. But the tricky part is, here's the thing. Now I'm going to disconnect this and connect it back because I'm not going to run that anymore. There's only so much this LED can take because we're going to go up to 24 volts in a minute. So if that's 43 watts, so if you check either wire here, the negative or the positive, it's going to give you that amperage. But the problem is that the energy is shuffling back and forth. So, some of the energy is going back into that battery. And then, if you check the wire here, like I showed, there was another amp difference. So actually the charging battery is actually sending some energy back into the system as well. And that's another whole thing to consider. So in other words, you've got this Y right here, right? You've got the positive coming down and teeing off with the negative here of the charging battery. So before the Y, it's a higher amperage, or no, it's a lower amperage than after the Y. And it all doesn't add up because amperage is just the wasted energy. It's when you close the loop. So here we have a complex floating ground open loop system. And so the amount of energy going to this battery, or this motor, is much higher now. And if we get everything phased just right, which we haven't tried to do all that because we're going to do that in another product. If we balance it all out, then this motor speeds up, the battery charges up, and then, hopefully you have this battery still charging at the same rate. So that's the third stage process idea in the very, very basic, the most basic demonstration that you can do. And so that becomes another, so the battery is a negative resistor, but also, See, that's still holding some charge there. But also this becomes a negative resistor. This is a negative resistance then as well. So it's a true negative resistor, not negative differential resistance. That's completely different. So that is that setup. Now let's move over to running it at 24 volts. So now I've got to put some jumpers here. And yeah, I'm just going to use some really silly looking jumpers here. Harbor Freight Special again. Only got time to do. I don't have time to make a perfect looking setup here. So we're going to put these in series, 24 volts. And now so you can hear it go again. Let's look at the amperage, everything. Alright, so I turned it down a little bit. Now I got to be really careful with this LED. What I think I'll do is go back to the resistive load because that's too much for those LEDs. For that LED, it's. Oops. So we'll go with these bulbs. I could put the 25 watt bulbs in there, or no, these are 15 watt. I got some 15 watt bulbs here rather than the 11. Let's start it off with the 11 and then we'll go up to the 15. And we'll turn this meter back on then again. Alright, so we're all good. Now this is going to go really fast. So I'm going to... We're still only at 4 or 5 amps. But you see we're at 246 volts. It's really too much. And I still don't have it turned up all the way. It's not enough of a load. We're running those bulbs too bright now. Oh wait, I got that only across one battery here. I gotta do this. This one. Alright, so there's that. So no matter what, if I go too high on this, see that's combined voltage, right? So it's not high enough. I'm going down there, I need higher voltage. And then that's too high. So it only could do so much. Okay, so what we're going to do 15 amp bulbs. And again, I'm using these really tiny wires and all that. It's not a very good example. So we want to check temperatures. I don't have the normal heatsink on this that I usually have. Just checking sure everything's okay. So you can see that's 15 watts now. And so we're more at the rating. It's still not quite right. If we were to go over to the LED, it would be really too much for it. I'll do it briefly. It's just way too much for it. I can't run it very long, it will burn up. Anyway, so now we're at 3.5 amps. Oh. I didn't have that at the right setting, sorry. So that's that, it's starting to flicker, it's not what we want for that bulb. So that's the single space setup. And now we're going to move over to the really high RPM. So we're going to disconnect the 24 volts now and go back to 12 volts. Because when this is going to fly really fast. When we get to the other model. Oh wait, what am I doing? We're not using any of these wires. Alright, so now we're done with this. We'll move this over. Here. Can you see that? Just kidding. Alright, so now we're going to run this model, the double stacked. Which I haven't run yet, so we'll see if it works. I mean, I ran it before, but I made some changes to it. So this is the generator wire. And I've got it so you can short it out right here. This is the damaged circuit actually. I've got it. There's no heatsink on this one either. Oh well. We'll run this and see what happens. Alright, so everything's good. See if I can get this connected again. Try and get the scope connected somewhere in there. Oops. Can't really get a ground connection. This cap's kind of in the way. Hopefully that does it. Alright, so this will be a double stacked. I didn't have time to do the double stack of this. Running out of time to get these videos done, or these orders out. Oops. Now I've got to place this in the right spot. Like I said, I haven't tested this one out, so I don't think it's going to run for some reason. Oh wait. Oh no. That's right. This one I have to move it over to the side. See, I'm not getting a good connection there. Yeah, this was the damaged board. So it kind of comes in and out. This is fairly high RPM. Oops. I think I got this up to about 9,000 RPM. Right now it's at 6,300, 6,400. Still rising. Alright, so let's look at some of these numbers here. We're only at 2.5 amps. We're not even... Oh. I've got to connect. .7. So that's all holding out, about the same. So now let's look at I don't know if I damaged this or what. Oh. That's why I had to switch the wrong way. So anyway, that's still appreciable light. And we're only at 2.36 amps at 12.5 volts. So depending on what you want to do, if you want to do the third stage process, this is really good, in which if you want to get a higher RPM and then put the coils in resonance with the output. So this is going to have no heat sink on there, but if I try and load this down a bit and see what happens. See, there isn't that much torque on this arrangement because this has become a traction repulsion motor. See, that's 5 amps. So this is not really good to do. But you still get the charging rate remains the same. So it's not good to use that as a torque motor. So this isn't the version that's a torque motor because the spaces are farther apart. But this is the high RPM. So if I didn't have this circuit damage, it's about 9,000 RPM that I got this up to at the 12 volt. This one's a bit better balanced now, so I don't really have to hold it. There isn't really much vibration there. I can't really get that connected up very well. Let me try and do this. So you can see it's the same waveform. And now we're at about 3 amps. Like I said, there's something on my pot here I gotta replace. So you can play around with it. We have different versions of this where the code where we can have more on time. But we created a limitation in the circuit so that when you put a load on it at a certain load, it will turn off. It'll be exceeding. So it's pretty fast. So anyway, that's 12 volts. Now we'll go back to 24 volts and then we'll run this big double stack one. So that one I had to move the hall a little bit. So let's talk about that for a minute while it's turned off, because you can't hear me as well. So if we want to, so I provided 4 spacers for the single and 8 spacers for the, 6 spacers for the double. So you could have 1, 2, 3, 4, 5, 6, it's 8 spacers for the double, and 4 for the single. So this is the double space. There's very little. There's not as much lock on there. Magnetic lock. It really glides over. This is the way we would have run the motors. The monopole motors would have been run this way. It's just a repulsion motor. As the magnet passes top dead center, we want to pulse it to push it. the way we were just running it with that motor over there was when we, it's a traction motor, it pulls in to the next pole piece, and that's where you get a lot of your torque. And then after top dead center you give it a push. And the thing about it is it takes a lot less to break the magnetic lock than it does to form it. And that's kind of the secret of these systems. So anyway, like I said, if we want to make the third stage process resonate with a certain RPM, presumably faster RPM, and we're not going to use the torque, we can use the generator coil action, but we're not going to load it down with an external generator, then this would be the preferable option. You can see very little amperage, and if we add that process again, it'll be really good. So let's go to 24 volts now, and we've got still a bunch more to show here, so gotta move on. Alright, so there's that. You can hear the tick. .25 volts, 25.29. So now this should just go real fast. Like I said, I can't really get connected there. If I run an extra wire, this isn't going to be quite accurate because of this added inductance, but I just don't want to mess that up. I can't really get a good solid connection there. So there's that battery still, you know, was charged to some degree for that short period of time. Alright, so let's get this going again. So I always look at the amps when I'm starting up. Oh. So I got to move the hull a little bit over. Oops. This is going to go very fast. The LED is going to blow out if I'm not careful. See that? That's that sound that's going up and down. I can't run this too long because I've got no heat sink on that. Anyway, you get the idea. Yeah, I forgot I got no heat sink on this. But it was okay, but I just didn't want to run it too hard. So that's 24 volts. Alright, so I'm going to run the double stack one now at 12 volts again. Still going for quite a while. This is more of a, I'm not going to be absolutely thorough in this video of what all could be done, but I did want to cover quite a bit of ground. I think covered most of it already. I just want to show, oops, these various systems running. So this has got the it's got the longer board because I've got the two FETs on there. This big, huge cable here. Alright, so we've got these wires all hooked up. So I haven't run this one yet since I made some changes on it too, so we'll see what happens. I'm going to turn it down a little bit to start. Alright, so we've got everything hooked up. Amp meters, voltmeters. You can see the battery still wants to come back, depending on what we're doing. Alright, so now we still got that LED hooked up. It's probably not appropriate to do that, but we'll run it for a bit like that first. And see, this one's really hard to turn. So you can see the waveform there. So we're drawing 7 amps here. It's pretty high. Still got to make some improvements on this motor with the programming and all that. So the charging rate's going to be up there. Should be up there. Now the lights out really, it's very bright, I can't even look at it. Yeah, it's kind of blinding. See, if I change the Hall, it will change. So anyway, that's that. We can turn this to the bulbs. See, that's drawing a lot more energy than it should. So we're going to put these bulbs on. These are oh no, these are the wrong ones. Yeah, I wanted to do the 15. Yeah, actually those were the right bulbs. Well, you can at least see $11-watt one anyway. Because it's clear, you can see it better, of course. But so anyway, that one, it's going to run better with the double spacing. Than it is with the single spacing. So this one needs a little bit more work than the single, because the magnetic, you've got south pole, oh, I should have said this earlier, the south pole facing up and north pole facing down. So the bottom rotor, the magnets, you can see the magnets facing up, and then these two rotors I have them facing down, but all the south poles are facing up throughout. So you have this one big, continuous magnet going throughout it. So it adds quite a bit more of a magnetic block. I mean, this is really, really tight, so it wants to be a little bit bigger gap. So that's why I was making the other one up, to finish that and show that connected, the double spaces, double layer and double spacing. So the one last thing I want to show then is going back to the first motor with the generator connected to it. Now we also have big Maxwell bank. So what I'll do is charge up this afterwards. You can see that bank there. So we'll leave that disconnected first. So this Maxwell bank is 1195 right now. So we'll show that in a minute. First we'll try this battery. Let's see how well this works. It might rumble around because I don't have it held in place very well here. Well, not at all. It may just flop around on me. Probably will. Might have to do it better. I'm not sure this is going to work. Oh wait. Let's plug this one back in. Now the problem I have that this leg has come off. Vibrating around too much. See, when I short them out, they put a dead load on it. So you can see it's charging up that battery, and we can, it's a bad demonstration here, but there we go. Alright, so now what we want to do is run our other loads, like we did before. So there's our regular load. Now try more amperage. Six amps. So it's charging the battery. we'll turn it down first. Alright, there we go. Alright, so now we'll turn it back up. So right now I only have a couple to the shaft. I don't have it properly secured. But that's the way it sounds when I clamp it with the. So you can see I'm charging up now more of the full extent. I can still load it down quite a bit more if I have more of a load. If this battery was bigger, you could charge it up. And of course I can load that down further. So we're still at 6 amps. Let me see the heat on this though, because I don't have. Yeah, we're still pretty good here. Alright, so now what we want to do is look at the Maxwell caps. So what I'm going to do, this is very dangerous to grab. So I figure which one's positive. Okay, so that is the right polarity. Oops. See, when these clips touch, so you can see it's charging up that big cap bank. These are 3,000 microfarad caps. In series, they are 500 farad, I should say, not microfarad. So they do charge up. Now this is not with the cap pulsar, like in this arrangement would be a much better solution. I just wanted to show that. So that's the arrangement for the generator. 6 amps. You can see it's charging pretty good. 1230 under load. Now if I balance this out more, I wouldn't be putting such a drag on there, but so it's charging up that cap bank. And there's curves of capacitors too. Oops. That you want to use. And again, you can regulate this by disconnecting one of these if you wanted to. Make it a two-phase. Alright, so now we're starting to get a little hot there because I don't have the regular heatsink on this one. Anyway, that is the arrangement. I'll leave that there, you can see. So we'll see that this charging battery has definitely charged up. The input battery has come down and it will go back up. We'll talk a little bit longer here to look at the voltages. We can see that this battery did charge some. Again, this is not some kind of attempt to prove output and input and all that. gives you a rough feel for it. I could have had different batteries here or whatever, but if I had this hooked up 24 volts, it might be nice to look at that. It's just, I would have to hook it a little bit better together here, move the shaft down and all that. I don't have time for that. So anyway, the idea here is, what I wanted to say in this video, among other things, is that I was trying to get away from previously from using a generator coil at all. But if I really want to push this motor to about 100 watts, input, then I have to load down the shaft more. The variac will not pull enough. Well, there still is more torque beyond what the variac can put a load on the motor. So if you want to do something like 100 watts for that, then at 12 volts, then you need to load down the shaft. So it runs around 4 amps at this particular setting, and then as we load down the variac a little bit, you can draw like 5 amps. That's about the max that the load you can put on the variac, because it is actually a additive system mostly. And then oops. So once you put the generator on, you can see, depending on the load, like when I shorted this out, which happened because these aren't really solidly connected, so they're moving around and touching, then it became a dead short here, and that put a much more of a load on this motor. So you can see what we've done is we've made this run so that it will go around 9-10 amps before it turns off. So that way it will protect the circuit, the MOSFET. If you want to run it at that higher levels, then you're going to want to make sure you have an adequate heatsink on the MOSFET. And I just have one of these clip-on ones here, heat sinks, not the one that I normally provide with the kit. So if you're going to run it to the extreme like that, then make sure you watch your heat. Otherwise, you can see that we're running this at 40 or 60 watts, and it was running cold, and still producing quite a bit of output. And but yeah, you can see the resistive load in place of the capacitive load, the various types of loads that you can run. You can see the difference between adding a spacer, a second spacer rather than the single spacer like this. This is more for the torque output. The other one is more for the higher RPM and for the tuning and all that. So you can make this motor run either way. And right now 12-24 volts, and we'll get to the 36-48 volts pretty soon here. And I think that should be it. Can't think of anything else to say. Yeah. So thanks for watching. Hope you enjoyed it.